Have you ever wondered what your daily wanderings would look like as a graph? Sounds a bit odd, doesn't it? I mean, do I really need to graph my stroll to the market? But trust me, graphs are like magic for making sense of how we move every single day. Think about it. Every time I walk, jog, cycle, or even jump on a plane, I'm actually creating a story. A motion story. And graphs? Well, they're like the comic strips of science. Instead of words or endless equations, I get a visual map of what's really happening. Take a distance-time graph, for example. If my line's going up smoothly, I'm walking steadily. If it gets steeper, I'm picking up the pace, maybe racing my mate to the shop. If the line goes flat, that's probably me stopping for a cheeky snack. Suddenly, what felt abstract makes total sense. And it's not just for us students. Scientists, engineers, and even pilots use these graphs to figure out if something's speeding up, slowing down, or taking a wild detour. When I see a curved line, it tells me things are changing. Maybe I'm dodging a cyclist or slowing down for traffic lights. So next time someone says, graphs are boring, just remember, they're the secret language of movement. Want to know how fast you sprinted to catch the bus? Or how long you stood waiting at the crossing? Plot it on a graph, and you'll see your journey come to life. Graphs aren't just shapes on paper. They're stories of our motion, turning our daily moves into real science. And who knows? Your walk to the market could be just as exciting as a rocket launching into space, at least on a graph.
We start by knowing our variables. We have distance, displacement, and time. A more accurate choice of variables are displacement and time rather than distance versus time. This may seem counterintuitive, but because velocity and acceleration are vector quantities, and a scalar quantity like speed isn't used to represent these concepts. Time is plotted along the positive x-axis due to the fact that time always moves forward. We use the y-axis to plot the displacement, distance from initial to final position, of the object. Let us use the diagram shown below. Point A is 5 meters away from point B. Point C is 2 meters from point B, and they are in a straight line. We travel from point A to point C in 3 seconds. We calculate the displacement to be 7 meters. We log it on our table. Say we go from point C to point B, we travel additional of 2 meters in distance in 3 seconds, but based from the definition of displacement is from initial to final. So from that statement, we calculate from point A to point B and get 5m of displacement. And so, if we travel from point B towards point A in 1.5 seconds, we add up 5 meters of total distance traveled, but we calculate the displacement from point A to point A and get 0 meters. We can now graph. We see that the highest value for the displacement is 7 meters, and for time is 0 to positive infinity. We plot one coordinates one by one and get. This line segment has its slope. The slope of the line segment in a displacement time graph represents the velocity of the object during that time interval. So from our slope formula, which translates to, we can now calculate for the velocity using the table. So we calculate the velocity for segment BC. Why is there a negative velocity? This means that the direction changed. And this is also the reason why displacement is used instead of distance. Distance is cumulative and can't signify direction change. So for segment CD, again the negative sign is due to the direction of the moving object. This is how we create the displacement versus time graph, and the slope of the line is equivalent to the velocity of the object during that time interval. We move on to velocity time graph. We will change the variables along the y-axis. This means that the quantity they modify is different. However, we can use the slope of the line segments in our displacement time graph. Assuming that the observer saw you walking with a constant velocity starting with t equal to 0 until t equals 3 seconds. This is when we travel from point A to point C in 3 seconds. We use the slope we get from the displacement time graph for the velocity during our travel from point A to point C. We graph it in the velocity time graph. Continuing the scenario, We go from point C to point B. We note that we reverse in direction. At that point, we momentarily stop going forwards and start moving towards the opposite direction. We graph and note that the line touches the x-axis, indicating velocity at that space, and time is 0 meters per second. And after that pause, we moved and our velocity is negative 0.667. We continue to head towards the initial position, but with faster velocity, and we graph it as. We see that this horizontal line indicates constant velocity. Whenever they appear or intersect the x-axis, the object is at rest. The length of the segments parallel to the x-axis indicates the time that it maintains this constant velocity.